Hello class, this is my presentation for exercise 5 from chapter 5. I want to apologize that I'm not able to be present in class for the presentations on Tuesday, but hopefully these slides will add something to the discussion anyway. So question 5 asks us to find the derivative of the function 2 sine 2 theta using the Fourier coefficients on the interval from minus pi to pi. And we also use the definition for the derivative as a linear transformation on the basis vectors of the Fourier space. We're also given the Fourier coefficients for our function as 2 over 2i if n equals 2, and minus 2 over 2i if n equals minus 2. Everywhere else, our Fourier coefficients are 0. And so we can write the coefficients in terms of this infinite vector, or we can collect the coefficients as a linear combination of our basis vectors, the powers of e to the I theta. And so we see a 2 in the second position and a minus 2 in this minus 2 position, telling us that the coefficients of e to the 2i theta should be 2, and e to the minus 2i theta should be minus 2. I would like to quickly recall this relationship from Euler's formula for the polar form of a complex number. If we let theta go to minus theta, and then we treat this as a system of two equations, then we can solve for either sine or cosine by adding or subtracting. Briefly, I'll mention we could also make this argument without loss of generality using de Moivre's theorem, but for the powers of complex numbers, but I won't go into too much detail about that here. You could basically imagine letting theta go to n theta, and notice that this agrees for our definition earlier, letting n equal to 2 for sine of 2 theta. So here's our definition for the differentiation operator in our Fourier basis. It's an infinite diagonal matrix going up to n in this downward diagonal and to minus n in this upward diagonal. If we recall our rule for finding the derivative of an exponential function, and we just sort of don't care about this I, then we'll see that the scalar of in pops out, which totally agrees with the different n powers of e to the in theta. We'll see more about that on the next slide, just to mention why the I shows up here and the n goes along the diagonal. And so what it really comes down to is this matrix operation. We can pull the scalars out since the transformation is linear with respect to scalars. So these i's are going to go away. And we'll end up with minus 2 times minus 2 in the minus 2 position of this matrix, and 2 times 2 in the second position of this matrix. We're going to leave the 1/2 out front for now, but we see that minus 2 times minus 2 is 4, 2 times 2 is 4, and we could also expand this out again as linear combination. And what we see is that this plus sign is exactly what we want to see for cosine, and the coefficients are now doubled, just like what we would see for the chain rule for normal differentiation for the trig function. Okay, and so that's all I've said here, basically just to wrap things up. I also think it's really neat that we could arrive here using our definitions from Euler's formula for the complex numbers, and finding these expressions for sine of n theta and cosine n theta. Okay, and so I'm sure it's been long enough, so I would like this is a place where I would take questions, and I would like to do so when I'm in class and we all meet up tomorrow. So I'll see you all then.